Good morning, ladies and gentlemen. Today I'm continuing with our discussion on LU decomposition, and I'm going to take you through a third method called the Cholesky decomposition. The Cholesky decomposition comes in a very special form. From the previous two videos, you'd realize that I always will tell you that we are solving the system AX is equal to B, and we want to write A in the form L times U, and for that matter, the name LU decomposition. Cholesky comes in with a very special way of decomposing the matrix A into L times U, where the U is equal to, only the U is equal to or is generated from the transpose of the L. So this makes it very special in decomposition. The reason is that you don't need to look for special variables to represent your U or new variables to represent your U entries, but rather the U is generated straight away from the L variables or the L numbers. So instead of writing L times U, Cholesky decomposition is usually represented as L times L transpose. This is the Cholesky decomposition. So we know that when you transpose the L, you get U. So instead of generating new values for U, Cholesky decides to transpose the original L and get the U out of it. And that is what is called the Cholesky decomposition. So as usual, I'm going to go for a smaller matrix as A11, A12, A13, A21, A22, A23, A31, A32, A33. This is my matrix, and the Cholesky decomposition comes in this form. Write the L, L1, 0, 0, L2, L3, 0, L4, L5, L6. So I have this, and instead of generating U using other variables or U variables, this time just write the transpose of the L. And so L1, 0, 0, L2, L3, 0, then L4, L5, L6. So you see, after transposing the L, we get a matrix that is an upper triangular matrix. So that is what Cholesky decomposition is all about. So you have the lower triangular matrix, which is made up of L, then the upper triangular matrix, also L, and so you just have L times the L transpose, where your L transpose represents your U. This is Cholesky decomposition. So as usual, you multiply the right side matrices into one, and then compare to the entries of the coefficient matrix on your left, and find your L1, L2, L3, L4, L5, and L6 for a 3x3 matrix, and then proceed with the usual steps in solving the system of linear equations using the LU decomposition. So let's do the multiplication and then analyze the answer. So we have this. L row 1 times column 1 will give us L1 squared. Row 1 times column 2 will give us L1, L2. Row 1 times column 3 will give us L1, L4. Then row 2 times column 1 usually would have been L2, L1, but allow me to write it L1, L2. Then row 2 times column 2 will give us L2 square plus L3 square. Then row 2 times column 3 will give us L2, L4 plus L3, L5. And with row 3 times column 1, again, I'm writing it as L1, L4. Then I have L2, L2, L4 plus L3, L5. And finally, I have L4 square plus L5 square plus L6 square. So this is the products of the two matrices on the right. And this particular answer we see on your screen help us to deduce some properties of the Cholesky decomposition and the kind of restrictions the solution methodology puts on the question or the kind of problems that can be solved. The first one to observe is the type of matrix we have as our solution. I can clearly rule out the main diagonal as this, and when you see this main diagonal picked out, I think it is clear to see that this particular matrix solution is a symmetric matrix. So clearly we have this entry being equal to that entry, the mirror. So the main diagonal is serving as our mirror line. This one is also equal to that one. So clearly we can see that this particular matrix is a symmetric matrix. So once the solution methodology produces a symmetric matrix, it definitely puts a restriction on the question matrix, which is the one we have on our left side of our equation, because if the A12 is not equal to the A21, then there will be trouble, because at the end of the day, we're going to say that let A1, L1, L2 be equal to A12. This particular entry will be equal to this entry. And then we can also say let this L1, L2 be equal to the A21. So if A12 is not equal to A21, then there is trouble. We are going to get contradictory mathematical equations or statements. And for that matter, once the solution methodology is symmetric, the solution methodology results in a symmetric matrix, it puts a restriction on the question or the kind of equation matrix coefficient that the Cholesky can solve. So the first thing that we need to note is that the Cholesky decomposition, being a symmetric matrix after the multiplication, means that the coefficient matrix must be symmetric. The coefficient matrix must also be symmetric. And that is a very, very important condition on Cholesky decomposition. Without symmetry, Cholesky decomposition will not work. And that is the first one. The second point to note is that if you look at this particular term, if you look at the first term on row 1 in the solution methodology, it also puts a certain restriction on the first term in row 1 on the question, because we are solving a problem that is more or less real life problems, because system of linear equations can come from real life problems, and we are looking for real solutions. And so if L1 square is going to be equal to A11, then A11 must be greater than or equal to 0, or strictly must be greater than 0. Let's put it so. Then A11 must be greater than 0. Or of course, in real terms, if it is equal to 0, there will be an answer to L11. So A11 being positive, must be positive. So, and other properties of the matrix must also prove to be positive, because you can see even the diagonal entries. If the matrix does not have a certain property of matrices, the diagonal entries, all of them have squares, and they are likely to cause us to find square root at some point. And that means that the matrix must have a certain special property that leads before Cholesky decomposition can work. And this property is what we call symmetric. So for Cholesky to work, we put the two together and say that for Cholesky to work, for the Cholesky decomposition to work, the coefficient matrix, must be symmetric, positive, definite matrix. This particular condition is very, very, very important. It has to be symmetric, positive, definite matrix. And this explains from the fact that after multiplying the right-hand side, the result is a symmetric matrix. And for that matter, the coefficient matrix must also be symmetric. And I've also showed to you that some properties of the matrix must also be adhered to become positive. And most especially to see it on the face of it, most especially the A11 must be positive. And that, putting everything together, we say that the matrix must be symmetric, positive, definite matrix. And that is very, very important in Cholesky decomposition. And that is what we're going to look out for in every problem that we're going to solve. So if that is not satisfied, convergence or even applicability of the, be able to, you can apply the Cholesky decomposition. So that is what we need to look out for before we try solving any system of linear equation using the Cholesky decomposition. So now that this is cleared, let us take an example and try to solve it. So this is an example. Later we'll discuss the whole idea of symmetric positive definite matrix in detail, where we will learn how to test whether a given matrix is symmetric positive definite, and that will be a topic on its own or in another video. So let's take this particular problem and try our hands on it. So first of all, what is my coefficient matrix? My coefficient matrix is 4, 2, 14, 2, 17, minus 5, 14, minus 5, 83. This is my coefficient matrix, and this is what I'm going to decompose. And then clearly, everyone can see that this is a symmetric matrix. This particular matrix is symmetric. And so first condition is satisfied, it is symmetric. For the positive definiteness, we can first of all look at this number, and it is positive. And so, of course, there is a chance that it will lead us to a positive definite matrix. So that is the first things we can look at for. So this, according to the product, has to be equal to L1, 0, 0, L2, L3, 0, L4, L5, L6, and times the transpose L1, 0, 0, L2, L3, 0, L4, L5, and L6. And from the multiplication, we had it to be L1 squared, then L1, L2, then L1, L4, then we have L1, L2, L2 squared, plus L3 squared, then L2, L4, plus L3, L5, then we have L1, L4, L3, L2, L4, plus L3, L5, then L4 squared, plus L5 squared, plus L6 squared. This is what we have. So because of the symmetry, you see that this particular guy may not be used, this may not be used, and this guy will also not be used. So we start with the first entry on row 1 and say that we have L1 squared is equal to 4. And this implies that L1 is again is equal to positive 2. I'm picking the positive 2 and not the negative 2 because once again, we need the result to be a positive definite matrix. We will not be able to use the negative answer of the square root. The reason is that if this particular value tends to be negative in the breakup, assuming this place becomes negative in the breakup, it may lead to a result that may not be positive definite. So we want to keep all our values from the square roots to be positive, and that's we have to have this one. So L1 is positive 2, then we have L2, L1, L2, that one according to the right, the left is 2. This implies that L2 is equal to 1 because L1 is 2. Then I have L1, L4 is equal to 14. And that implies, because my L1 is 2, L4 is 7. Then I have L2 squared plus L3 squared is equal to, the middle number there is 17. With this, we can say L2 is 2. That gives us 4. Let the 4 go to the left-hand side to subtract. So L2 is 1, which is here. So 1 square gives us 1. Let it go there to subtract, and that gives us 16. And so L3 is square root of 16. And once again, I take positive 4. Then the next one becomes L2, L4 plus L3, L5 is equal to, the value there is negative 5. What do we have? We have L2 to be 1. We have L4 to be 7. Then we have L3 to be 4. And we don't know L5. And that gives us minus 5. This gives us, this is positive 7. Take it there to give us negative 12 divided by 4, and it implies our L5 is negative 3. Then finally, I go for L4 squared plus L5 squared plus L6 squared is equal to 83. 83, L4 is 7, so 7 squared plus L5 is negative 3, so negative 3 squared plus L6 squared, that is 83. This is 49, 49 plus 9, that will give us 53. So subtracting 49 plus 9 will give us 58 rather. Subtracting 58 from 83 will lead us to L6 squared to be 25. And so our L6 is equal to 5. So now we know our L, and then we can write our L and write our U, which is L transpose. So we have L to be equal to L1 is 2, 0, 0. L2 is 1. L3 is 4, 0. L5 is L4 is 7. L5 is minus 3, and L6 is 5. So this is what we have. And that implies our U, which is L transpose, is going to give us 2, 0, 0, 1, 4, 0, 7, minus 3, 5. And as usual, we are going to just use this new matrices, the L and U, or the L transpose, to solve the system on your screen, the left side of your screen. And how do we solve that? As I outlined in my previous videos under Doolittle and Crowd's decomposition, we are solving as usual A, X is equal to B, and you have changed your A into L times U, X is equal to B. And so we said that set this guy to be equal to a certain Y, which has the same size as X, or the same length. So we're going to solve Ly is equal to B. And when we get the answers to Y, we come here and solve Ux is equal to Y. So first of all, let's solve Ly is equal to, so Ly is equal to B, where my Y is a vector of the same length as X. And so I'm going to have it as 2, 0, 0, 1, 4, 0, 7 minus 3, 5 times Y, which is Y1, Y2, Y3, because X is X1, X2, X3. The B part, which is the right-hand side of the system, is 14 minus 101 and then 155. This is what I have. And writing this into equations, we're going to have 2y1 is equal to 14, y1 plus 4y2 is equal to minus 101, then 7y1 minus 3y2 plus 5y3 is equal to 155. So this is what we have. And clearly, this is easy to solve, as I explained previously. So from equation 1, we can find y1 to be 7. When y1 is 7, we're going to have it in equation 2 as 7 plus 4y2 is equal to minus 101. Take the minus 101 to, take the 7 to the right hand side, and that gives us 4y2 to be equal to minus 108. So my y, it implies that my y2 is minus 108 on 4. And that gives me minus 2 minus 2 28 gives us 7. So 27 minus 27, and that's is the value for y2. Then y3, so substituting into the equation 3, we're going to have it as 7 into y1, which is 7, minus 3 into y2, which is minus 27, plus 5y3 is equal to 155. So this gives us 49 here. This gives us positive 27 times 3 is positive 81, plus 5y3 is equal to 155. So put everything together, this gives us 135, sorry, 130. This gives us 130, and take that 130 there, it gives us 5y3 is equal to 25. And that implies that my y3 is actually 5. So this is what we have. And so we can proceed to solve the other system that comes out of the u. So now that we know our y, we're solving ux is equal to y. And so u is, according to the system, the transpose of L. And so we have 200, which is 140, and then 7 minus 3, 5. Then this multiplies our x1, x2, x3. That is what we are looking for. The y was just an intermediary vector to help us solve for our x. y1 is 7. y2 came out as minus 27, and y3 is 5. So this is what we want to solve. And so from putting it in equation form, we get 2x1 plus x2 plus 7x3 is equal to 7. Then 4x2 minus 3x3 is equal to minus 27. Then finally, 5x3 is equal to 5. So solving this particular system from equation 3, the third equation, our x3 is equal to 1. And if x3 is 1, then we go into the second equation and get 4x2 minus 3 into 1 is equal to minus 27. And take this positive 3 to that side, gives us, if we take positive 3, sorry, negative 3 to that side, become positive 3, and that reduces it to negative 24. So we're going to have 4x2 is equal to negative 24, and that implies my x2 is going to give us negative 6. So if x2 is negative 6, then we have, putting it into the equation 1, all the 2, so we get 2x1 plus negative 6 plus 7 into positive 1 is equal to 7. So this simplifies, the left side constant simplifies to positive 1, which goes there as negative 1, and that gives us 2x1 is equal to positive 6. And so our x1 is equal to 3. So that means our solution vector x, which is equal to x1, x2, x3, is actually given as 3, negative 6, 1. This is the solution we are looking for. 3, negative 6, 1. And that is what we are solving for. So this is the solution to the problem going through the Cholesky decomposition, and particularly the very first approach that helps us to solve the system. I will explain another approach to those who are very familiar with the Gaussian elimination and prefers the use of Gaussian elimination in solving systems of linear equations. You can still use Cholesky decomposition and pass through the Gaussian elimination approach to get your answer. And that is what I'm going to explain in the second approach. So approach 2, as I always do, my approach 2 is dependent on Gaussian elimination. With it, before we move into the approach 2, first of all, we need to understand that after the decomposition, for a symmetric matrix, or even before, note, let me put this as a note before I go to the approach 2. We should note that for a symmetric matrix, A, if we decompose a symmetric matrix using the Doolittle approach, we are going to have the L of the Doolittle times the upper of the Doolittle after the decomposition. Because I'm going to use the Gaussian elimination, we all know that the Gaussian elimination is more or less a Doolittle approach, as we saw in our previous discussion. So whatever approach that depends on Gaussian elimination is more or less dependent on the Doolittle decomposition. So that is why I want us to look at the relationship between the decomposition, the crowds, and the Doolittle matrices. So this is the decomposition, but this can be written in a form L for the Doolittle, a certain D matrix, let me call it diagonal matrix, a certain diagonal matrix, a diagonal matrix whose diagonal entries are just equal to the entries, the corresponding entries of the upper triangular matrix, the corresponding diagonal entries of the upper triangular matrix of the Doolittle. When you extract that diagonal matrix, then the upper triangular matrix left becomes Doolittle lower triangular transpose. This is an observation that you can make from a symmetric matrix when you pass through the Doolittle decomposition, and it is verifiable. that when you do the decomposition and you extract or you factorize the diagonal matrix out of the upper triangular of the Doolittle, the upper triangular matrix that is left becomes the transpose of the lower triangular matrix of the Doolittle. So it tells you that for a symmetric matrix, the upper triangular Doolittle is actually a certain diagonal matrix times the lower triangular transpose of the Doolittle lower triangular matrix. And this is a very important observation. So we can make use of this identity to quickly generate the Cholesky decomposition. The reason is that this D that we see in there, we can split the D into two because now we have the diagonal matrix, the lower triangular matrix here, and that lower triangular matrix is transpose is here. So if we're able to split this D into two and bring part to the lower triangular matrix on the left and bring the other part to the upper triangular matrix on the right, they will all result in a lower triangular matrix and an upper triangular matrix, which is actually a transpose of the lower triangular matrix. And that is what we're going to do. And that is the move we want to use to get the Cholesky decomposition. And that, so look at this one. So we can rewrite this one as LD, which is the Doolittle. This time, let this find the half D exponent half out of the D and get D exponent half for the upper part, and we have this. So this new product, this D is also a diagonal matrix, but this time its entries are square roots, positive square roots of the original D. So D half, D exponent half is a diagonal matrix. It's a diagonal matrix whose entries are just the square roots of the entries of the diagonal entries of the upper triangular matrix of the Doolittle. So now, if we multiply this and that, you get a certain lower triangular matrix. And when you multiply these two, we'll get a certain upper triangular matrix, which is the transpose of the lower triangular matrix. And this decomposition, as we know from beginning, is what is known as the Cholesky decomposition. So by this, we can say that we can pass through the Doolittle approach of finding decomposition to get the Cholesky decomposition, where we'll find our decomposition using Gaussian elimination, look for the L of the Doolittle, then look for the D half. Once we get the L of the Doolittle and the D exponent half, we can find the L of the Krauts and the L transpose of the, we can find the L of the Cholesky and the L transpose, which becomes our upper triangular for the Cholesky. And that is the approach we want to go. So first of all, you look for the Doolittle lower and upper triangular, generate the D half, which is the diagonal matrix that has its diagonal entries being the square root, positive square roots of the diagonal entries of the upper triangular of the Doolittle, and then it proceeds to help us multiply the L times the D half to get the L of the Cholesky, and then its transpose will definitely give us, or even the D half times the L transpose will give us the L transpose for the Cholesky. And that is what we need to note. So now that this is clear, let's look at how we can use this approach. Let's look at how we can use this approach to solve the Cholesky decomposition. It is going to give us this. First of all, we need to use the Gaussian elimination to find our lower triangular and upper triangular as if we are doing Doolittle. And then we will come and use this mathematical identity or ideas to find our lower and upper for the Cholesky. So I'm going to go for my A matrix, and that A matrix is given by 4, 2, 14, 2, 17 minus 5, then 14 minus 5, 83. This is equivalent to, through Gaussian elimination, we are going to have 4, 2, 14, and then the row 2, we're going to have row 2 to be equal to row 2 minus the Gaussian factor there is 1 over 2 row 1. So let's do that multiplication somewhere. I have 2 17 minus 5. 1 over 2 times row 1 will give me 2 here, 1 here, and 7. Subtract, and that gives me 0, 16 minus 12. So 0, 16 minus 12. And then row 3 becomes row 3 is equal to row 3 minus 7, sorry, 14 on 14 over 4, which is 7 over 2, row 1. And that's, we have 14 minus 5, 83. So 7 over 2 times row 1 will leave us here to be 14. That will be here 7. And then we have there to be 2 goes there, 7, and that will give us 49. So subtracting, we get here 0 minus 12. Then when you subtract 49 from there, this gives us 4 here, and we have 34. So we get 0 minus 12 and 34. So this is what we get after the first iteration of the Gaussian elimination. Then the next iteration, our pivot is now 16. We get 4, 2, 14, 0, 16 minus 12, and that row 3 is equal to row 3 minus negative 12 on 16 will give us negative 3 on 4, row 2. And that's, when we do that, we're going to have 0 minus 12, 34, negative 3 on 4 times, this will give us 0, times that will leave us with minus 12, and times minus 12 will give us positive 9. And when we subtract, we're going to have 0 here, 0 here, and this will be 25. So we have 0, 0, 25. This is the upper triangular of the Doolittle. Notes. So we have the upper triangular of the Doolittle, and we can generate the lower triangular. So we have the L of the Doolittle. Let me so denote it as that. and that is going to give us 1, 0, 0. Don't forget the half here, the Gaussian factor used over there, then 1, 0. Then the Gaussian factor used here is 7 over 2. Then Gaussian factor used here is minus 3 on 4, 1. So this is the lower triangular of the Doolittle. And the upper triangular of the Doolittle is actually 4, 2, 14, 0, 16, minus 12, 0, 0, 24. In actual fact, I don't need all this. All I need is the diagonal entries of the upper triangular. So I could have just gone ahead to write this lower triangular and then extract the diagonal entries to form my D half. That is, I need only the D half and this lower triangular. According to the identity we have over here, I need only the lower triangular and the D half. That is all I need. So once I get them, I can find my, so I'm going to restrict myself to the Cholesky decomposition and will not go back to explain the concept I've given up there. So all I need is the D half. So D half is going to be a diagonal entry that has the entries, the diagonal entries being the square root of the corresponding diagonal entry. So this is 2 here, 0, 0, then 0. This is 16, and so we get over there 4, 0, 0, 0. This is 25, I think, 25, and I wrote 24. So 25, and so the entry there is 5. So this is what we have. So now, what is our lower triangular for the Cholesky? The lower triangular for the Cholesky, if I can denote it by LCL, then it's going to be 1, 0, 0, half 1, 0, 7 on 2, minus 3 on 4, 1, times 2, 0, 0, 0, 4, 0, 0, 0, 5. When you multiply this one, we're going to have row 1 times column 1 will give us 2. Row 1 times column 2, 0 times column 3 is 0. Then row 2 times column 1 will leave us here 1. Row 2 times column 2 will give us 4 here. Row 2 times column 3 will give us 0. Then row 3 times column 1 will give us 7. This times column 2 will give us minus 3. And row 3 times column 3 will give us 5. So if you look at this L, clearly it is the L of the Cholesky before. And for that matter, we can find our U for the Cholesky, which is L transpose, L Cholesky transpose, which gives us what? 2, 0, 0, 1, 4, 0, 7, minus 3, 5. And then proceed as we did in the previous case. So this particular matrix is the same as that matrix, as the same as this matrix that we had over here, the lower triangular matrix we had over there, this one. They are the same. In the same way, the upper we generated from the transpose is the same as the upper we will get from here. So if you are someone who is very conversant or very good in the use of Gaussian elimination, then you can find your Cholesky decomposition by passing through Gaussian elimination. Just do the Gaussian elimination method that we use for finding the Doolittle decomposition matrices. So find your L, particularly the L, and then for the upper triangular, just pick the diagonals, the square root of the diagonals, and form the D exponent half matrix. D exponent half matrix. Once you have your D exponent half matrix, you only multiply LD, or the L of the Doolittle, by the D exponent half matrix, and you get the Cholesky L, which can be transposed to produce the Cholesky upper triangular matrix. The identity I explained over here, you can prove that simply, and you see clearly that if you multiply the D half by the transpose of the Cholesky, or when you extract the D half out of the upper triangular, it will give you the transpose of the Doolittle. After that, you split it into two, and you see as for this multiplication, we have seen that it is so. As a student, just try and multiply the D half by the transpose of the Doolittle lower triangular, and you see that giving you the transpose of the Cholesky the transpose of the Cholesky lower triangular. So these proofs can be verified easily using the same example that we have outlined. So you can go through Gaussian elimination, produce the lower triangular of the Doolittle, extract the diagonal entries of the upper triangular to form the D exponent half matrix, and multiply the D exponent, the L by the D exponent half to get your Cholesky lower triangular matrix, and you transpose that lower triangular matrix to get your upper triangular matrix. Then proceed solving the problem as we did in the previous methodology. And that is a very important approach that those who are very conversant or very good with Gaussian elimination can also proceed to use to find the Cholesky decomposition. And with this, let me bring you to the end of this particular, with this we end this particular video, and then we'll meet in a subsequent video to discuss the symmetric positive definite matrix. We need to understand what a symmetric positive definite matrix is, so that when the problem is given to you, you can assess whether Cholesky can be used to solve it or not. Thank you very much, and see you in the next video.